Okay, there we go.
Okay.
All right. Well, thank you everybody for coming. So we're going to hear from Dorothy about Mars. But before I do, I just want to say that Battle Point Astronomical Association is we're a nonprofit and we operate here. This building belongs to the Park District, and so but we have a long-term lease to be here, and the telescope on the roof is ours, and it's all the equipment in here. We have star parties every month, at least every month. Second Saturday, like tonight, we have a speaker and then we'll have a star party. But sometimes, if the weather permits and some of our volunteers feel up for it, we'll have an impromptu star party. And the way to find out about those is to become a member, because we have a secret email list that we use to notify folks at the last minute, you know, a day or two, or maybe even a couple of hours in advance. Hey, we're going to be out at the observatory, come on out for a star party. So, so you might think about becoming a member. It's pretty inexpensive. It's $20 a year for an individual and $30 a year for a family membership. The other thing that we're doing is this big tower that you see over here, the boxes on top of it, that platform used to support our planetarium projector that shines up on a dome that hangs from the ceiling. The projector died, so we took the dome down, which is why we have echo in the room. But we're trying to raise money to buy a new projector, and that's a $60,000 proposition between the projector and the software and building a new dome for it. We just received a $15,000 grant from the Bainbridge Community Foundation. We have a member has pledged $15,000 as a matching grant. So now, as people make donations, those will be matched 1-for-1, and hopefully by the end of the year, we'll be able to raise the $60,000 that we need. So if you feel like throwing in $100 or $1,000, whatever, $5, $20, or $30, I've got a Square device here, and it will take credit cards, or you can throw some dollars in the pot, and that will help us restore our planetarium capability, which is how we reach a lot of people in our cloudy, rainy winter nights. We can still have programs in here with the planetarium, and it's especially popular with kids. So, so hopefully that'll happen, and if you feel so moved, please support us. Great, thanks.
Nice.
Dorothy, I think that's about all I wanted to say. So I'll hand it over to you.
Okay, I'm going to share my screen and
Hang on just a second. Sorry, I've been reminded that there's one other announcement I need to make. On Tuesday morning at 7:30, we're going to be open here. You might have seen the sign outside. The James Webb Space Telescope first images are going to come in. And hi, come on in. The James Webb first images are, and we're going to stream them on the screen here at 7:30 in the morning. So come on in and bring your coffee or whatever, and we'll do that. And then later in the afternoon, there will be NASA will have an expert panel of people who are going to tell us about the images. What are we actually seeing in those images? And so that'll be at 3 o'clock in the afternoon. So after you've come here at 7:30 to see the images coming in, you can go home, take a nap, and you can come back at 3 o'clock and listen to the expert panel. So that's coming up this week. Okay, take it away, Dorothy.
okay, I'm going to share my screen. Let's see if it works. Let's see, I need to go to here. And I want to do this. And
there you go. That looks good.
And are all the images still on the screen? Do I need to get
everybody's gone. All it is your slide.
Okay, I need to get rid of them so I can see. Maybe make sure I do the right thing. Okay, I can see. Well, hello everyone. It's nice to be here. You may know I gave a similar talk to this one about 8 months ago to the Italians in America group in Houston, which is where I live. So what I've done is I've updated the talk. A lot has actually changed in 8 months. And I added a little bit more science since you're a science-oriented group of people. So I added a little bit more science, but not a lot. So hopefully you will still find it interesting. So this is a picture of me a few years ago at Johnson Space Center, where I worked for 13 years with my boyfriend, Robonaut. Robonaut has been sent to the International Space Station, where he will spend the rest of his life helping with some of the outdoor repairs and things like that. So that's Robonaut. So let's go to Mars. I don't think I need to tell an astronomy group where Mars is in the solar system, but I did just want to point out that on this close-up here of the close-in planets, compared to Earth, Mars is much smaller. It's about half the diameter of the Earth, and that means it has quite a bit lower gravity, and today it has a thinner atmosphere. You probably also know that the Earth is often referred to as a pale blue dot, and I'd like to just show you this particular image where the Earth was first observed. And this is an image from Voyager 1 that was actually taken in 1990 at the request of Carl Sagan. Voyager 1 was about to leave the solar system. Carl Sagan requested that it turn around and image the Earth. And that is the first view of Earth from the solar system. It's so small. But that's and Carl Sagan coined the phrase pale blue dot. So that's where that comes from. So if we go to the next slide and just talk about Mars now. Mars today is the red planet. And you can always tell Mars, it has this enormous scar on it. It's a huge fault system. And you can always tell it's Mars by that. But Mars today is a very cold planet. It's farther from the sun than the Earth. Average temperature minus 81 degrees Fahrenheit, but it goes as low as minus 220 in places. The atmosphere is thin, maybe just 1% of Earth's today, and it's mostly CO2, so it's a very different composition. The gravity is about 1/3 of Earth's, and because of the thin atmosphere and the cold temperatures, liquid water is not stable on the surface of the planet today. And the surface we know is red, and that's mostly because of oxidized iron, so it's like a rust. But if you look at the image in the lower right, you can see the scar. This is Mars, and this is an artist's rendition of what Mars may have looked like 3 billion years ago, early in its history. It may have been a planet with oceans where it's blue, or lakes and ponds with clouds, rainfall, and snow. So that's really what I'm going to be talking about, because there is a lot of evidence related to that. And of course, then the big question is, was there ever life on the red planet? And the answer is maybe. And it's because of that early history when it was much more amenable to life, much more habitable than it is today. And you'll understand that better as we go. So how do we get our data from Mars? There's two kinds of data. There's orbital data from spacecraft that are orbiting around the planet, and there's ground-based data. First, to talk about the orbital data, there are now 7 orbiters orbiting around Mars. It's amazing. It's really changed a lot, even in the 8 months since I last gave a similar talk, and that's because the Chinese and the United Arab Emirates have launched orbiters. Now, each of these orbiters is doing a different type of thing, gathering different types of data. And this one is colored blue because it's actually not active anymore, but it is still in orbit. But Mars Global Surveyor was active since 1996 to 2006. And it has provided some of the most useful data, and I'll be using a lot of this and talking about it. It's called MOLA data. It's really Mars Orbital Laser Altimeter data, which gives us the topography of Mars, and I'll be showing you a lot of that. So I'm going to be talking about that. I think I may mention some infrared data. And I'm going to mention a lot of high-rise and context and CRISM data from Mars Reconnaissance Orbiter, which is one of it's the most recent NASA orbiter. 2006 was launched and it's still going strong. And these are some of the highest resolution images of Mars that there are. So that's what I'll be talking about. So let's go now to Mars. Let's see what we know. This is a projection that shows you the entire planet. So there's nothing behind, no back. We see everything in this. And this is MOLA data, that Mars Orbital Laser Altimetry data. So it's topography. And the color scheme is such that the reds are the highs. And you can see here we go up to 3,500 meters in height. And the blues are the lows, it goes down to minus 4,500 meters. And I have colored this happily blue. It looks like an ocean, but it's not. Right now, the whole planet is dry. But you can see the planet basically has two halves, the southern highlands, that's generally high, and the northern lowlands. And some people think, and there's a lot of evidence suggestive that there may well have been an ocean at one time in this whole northern hemisphere. And the two hemispheres are divided by this very striking, very quick change from the highlands to lowlands that's called the Martian dichotomy. And it's interesting, oops, I want to go back. That happens to me a lot with this presentation. This area here, that's a very, very high area, is a huge shield volcano. And actually that's the reason for this big scarp, because it bulged the crust up. But it's a fairly young, relatively young phenomenon, and the formation of the dichotomy is thought to be the earliest thing that happened on the planet. So this has changed the way that dichotomy looks, and one person did a really nice scientific study. If you remove the Tharsis uplift from the planet, you'll see that dichotomy going all the way around the planet. It looks like a huge elliptical impact onto the planet. And that's what people think now caused this separation into the two hemispheres on Mars. So let's go to the next slide. Okay. So this is the same view. And this shows you some of the ground-based data. We have both landers and rovers. The landers are shown in the white triangles, and the rovers, the things that move around from place to place, are shown in the red triangles. First, let's just talk about the earliest landers with Viking 1 and 2. They're shown here, and you can see where their locations were. This was 1976. And then the next thing that NASA did was the very first rover, that was the Mars Pathfinder with Sojourner. Sojourner is the name of the rover, 1997, more than 20 years later. And that's located right here. I'm going to talk a little bit more about Pathfinder because it's an interesting story. But right now, I just want to cover all of these real quickly. You may remember the lander called Phoenix. That was in 2008. It's the one where it landed, and one of the legs exposed some frost. And that was kind of exciting because it proves that there's still ice very close to the surface in some places. And the other ones you may have heard of are Spirit and Opportunity. Here's Opportunity located here, and here's Spirit right over here. Both of them lasted much, much longer than they were planned for. I think they were planned for 90 days, and Opportunity lasted for 14 years. A tremendous amount of data, probably the first really significant data that was strong evidence for a past history of water on the surface of the planet. So that was from Opportunity. And the ones, more recent ones are Curiosity, which is located right here. The actual crater is right next to the triangle. I didn't want to cover it up, but that's the crater, Gale crater. We'll be talking about that in detail. I was on the science team for the Curiosity rover for 5 years, so I do know a lot about that one. And Perseverance, the most recent rover mission, is located here, and I'll be talking about this one too, because the two are providing huge amounts of data. The other interesting thing that you might want to know about is that the European Space Agency has had a project called ExoMars 2022, and they were going to land right here and drill to 2 meters in depth. That would have been an absolute first, and it would have been so important and interesting. Everything else, even Perseverance and Curiosity, only drill 6 centimeters into the surface. We've got a lot of information from it, but 6 centimeters is nothing in the scope of things, particularly on a planet with a lot of potential radiation damage on the surface. So that was really exciting, but the project was actually a joint project between the European Space Agency and the Russian Space Agency, Roscosmos. I can never pronounce it well. But because of the Ukraine situation, that has been canceled, and it's actually disastrous. There are all sorts of people in Europe who have spent more than a decade preparing for that, and they're just devastated right now. There's possibilities that it may be brought back on with the next landing opportunity in 2024 or 2026, but it's not at all certain right now. So it's a big disappointment. Okay, so that's good. I just put this on to show you some of the different rovers and the comparison. The very first one that I mentioned, Sojourner, looks like an absolute baby compared to the others. This is Spirit and Opportunity were this big, and this is Curiosity. And I didn't put Perseverance on here because it's about the same size. Perseverance was basically based on the Curiosity rover, 6 wheels, a mast with the cameras, and an arm that has the drill and some of the close-up cameras. So Perseverance is very much the same. Okay, so just to go back to Pathfinder for 1 minute and the Sojourner, that very first rover, we got back some images of this area, and you could see that people might have thought it was in where an ocean might have been. It looked like a really good landing place. It looked like possibly rivers were flowing out here. And, you know, honestly, I remember when these images came back. This is one of the typical images from Pathfinder, and it looked dry and like there were a lot of rocks and boulders. It just didn't look like people had hoped it might look like. And I think there was this feeling was, oh, the whole planet is just rocky and whatever, it's all red. There's really nothing much interesting happening there. So what I'm going to tell you is that view is completely wrong, and that's what we'll be talking about today. So the view today of Mars's history, if we just look at this top panel, if we go from the beginning of when most planets were formed in our solar system, 4.5 billion years ago, it is thought that Mars was wetter than it is today. It was a wet planet. It may have been cold or warmer. That is still in some dispute and discussion, but everybody agrees that the planet was wet. There's strong evidence for rivers, even glaciers, and possibly the ocean. And we know today that it's dry and cold. This is today right here. And we think it's been dry and cold for quite a long time. And then there is a transition period. But if we look at microbial life on Earth, if we just plot it out here in the same time scale from today to when we know that it first evolved, we know it at about 3.6 or 3.7 billion years ago. And that's probably not the oldest. It's just that on Earth, we don't have a lot of examples of the oldest rocks because of plate tectonics. But Mars does not have plate tectonics. So first of all, life may have evolved a little earlier on Earth. It certainly evolved a little bit earlier than our data. And if you notice that Mars may have been wet into the period when we know that microbial life evolved on Earth. So if it evolved on Earth before, say, 3 billion years, then it may have evolved on Mars as well, because the planet was very Earth-like in its early history. It may have been a blue planet that was habitable like the Earth was, and now it's a very different planet. But so that's what the general thinking is today of the history of the planet. Okay, and now just for some real gross overview of some of the evidence for rivers and whatever. Okay, here's the scar that I mentioned, the big bulge in this shield volcanic area. And if you zoom into this area here, and and you stretch the colors from the topography so you can see a little bit more detail, it looks very much like rivers just flowed from that scar into this basin and then further. And for people that studied fluvial systems, river systems, they would tell you that the first places where it goes into a body of water would be where the coarse grained sediments would drop out. So it's not surprising at all that Pathfinder had a lot of big rocks and boulders. But the fine grained sediments, the muds, which is where water would have been longest lived and where likely chemical fossils of potential life would be preserved in those fine grained muds, they would not be in this area. They would be farther downstream in the deepest areas here. In this scale here, the purples or the hot pinks are the deepest. So the fine grained muds would be here. So that gives us a little more insight to why Pathfinder looked the way it looked. And still very good evidence for a huge river system. And they think actually that this scarp opened up an area that might have had ice and it warmed the ice. Whoops. As I say, that happens a lot. It warmed the ice, and these were not only rivers, but floods bigger than any that have ever occurred on the earth, they think. So there's also strong evidence for glaciers. I find that these images amazing. This is Mars, and there is nothing on Earth that can produce a feature like that except glaciers. These are 3 glaciers from Canada. What's really typical about them is that they have a terminal moraine where they stop flowing. They've carried debris and ice, and because it's flowing down this channel, it flows in these kind of arcuate, almost circular endings. And so you can see those similar things here in Canada. And these linear grooves, again, that's ice flowing down this channel. And you can see a hint of those grooves here, and you can see some of those grooves in this one as well. Those are really characteristic. Rivers don't do that. Lava doesn't do that. And there's a few other characteristics, but to me, that's absolute evidence that there were glaciers on Mars. It's not a glacier now, it's covered with debris, but it's kind of like the fossil of a glacier. So I find that very exciting and interesting. Okay, but so now let's talk about Curiosity. As you can see, it's right on the dichotomy, and that was one of the reasons it was selected, because it's a very unusual place. It may have had a little more water than other places being there because, in fact, the dichotomy has a lot of faults associated with it. So possibly water came up from depth. So Curiosity landed on Mars in 2012. And this crater is called Gale Crater, that's the name of it. And the main goal of that mission was to determine if the planet was habitable. In other words, did it have water for long term, enough water to actually support some sort of development of life? And did it have the key elements that we know life needs? And that's carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus. So those were the main goals of that. So let's talk. So here's another image of Gale Crater. That's the crater we're talking about for Curiosity. Here's the crater rim. This is a different color scheme, but again, the reds and yellows are the highs. This is a low area here, and you can see that the crater has a central peak area, which is common in big craters. This is a big crater, 155 kilometers in depth. And this red oval was the landing ellipse. In other words, that's the place that the Jet Propulsion Laboratory, JPL, determined was the place that would be safest for the spacecraft to land. They always look for flat places, places without many rocks and boulders, and places without great slopes, because they have to land safely for anything else to happen. And so even though the main objectives were not here, they were actually out in this area here, which I'll show you later, they couldn't possibly land there. So all of the missions have this issue. They have to land in a flat place that's safe. Where they actually ended up in that ellipse is where the green triangle is shown. That was their actual landing place. And it's not known exactly where it will land until they actually land. They know it'll be in that ellipse somewhere. And there was funny stories about the landing ellipse, but I'm going to leave that up for now. One other thing, just to mention, the rover itself, you know, it had the 6 wheels, and this is a close-up of one of the wheels. The people at JPL did kind of a fun thing with the wheels. Each wheel had these patterns on them, and this, believe it or not, is Morse code for JPL. This is dot dash dash dash, that's J. This is P dot dash dash dot, and this is L dot dash dot dot. So, but it was more than just fun, because as the rover travels, the footprint of those dots and dashes can be seen on the ground, so they can measure. It gives them another way of measuring the distance that the rover has traveled. Okay. So, as I said, the objectives were not really in that landing ellipse. And here you see the bottom of that ellipse here, but they were further to the west. In fact, from the landing ellipse, the landing site, which is up here, we had to come this way, cross over these black sand dunes. These are enormous dunes. Come this way, cross over this thing that looked like, we called it a fence initially, and come into this region here, which is a region where we have information that there was clays in this region. And that's where we hope to find the most organic matter, which could be some of the best types of materials to find biosignatures if they're there. And then we were going to come up this channel here. So let's just go. So we landed, and the very first thing that happened is, if you look here, this is one of those high-rise images. If you remember, I mentioned that from Mars Reconnaissance Orbiter. These are some of the highest resolution images we have. Here's the landing ellipse, and here's the landing site. And you could see that this channel and what looks like an alluvial fan comes right into that area, and we're right on the edge of that. And if you look at that same area using that infrared data that I mentioned, it showed that the thermal inertia in this area was different than everything else, almost as if one could imagine water and sediments coming down this fan and ponding here in this low area, and then maybe evaporating and leaving a different type of material there that would have a different thermal inertia. So the science team all together decided that the first thing we were going to do, since we were so darn close where we landed, was not to go west, but was to go the opposite direction. And we just had to go here and see what that was. And so that's what happened. And this is another high-rise image. It's a close-up, and it's from one of the color images, which are even higher resolution than what I just showed you. Here's the landing site. Here's 150 meters now. And here's that area with the different color thermal inertia. And we got to this area, and it was called Yellowknife Bay. And you may have even heard of that. You'll see it in a lot of publications, and you'll see it more in this talk. But so we got into this area. It looked like perhaps the area of longest lived water in the crater, because it was one of the lowest topographically points of the crater. And since Mars does not have plate tectonics, unlike Earth, what you see today in Mars is very much like what it was 3 billion years ago. So that's pretty exciting. And in fact, it's one thing that makes Mars geology much, much easier than it is on Earth. So the next few slides, so we went this way initially, even though the primary objective is that way. So we had some information from a site here, and then we actually drilled here in Yellowknife Bay, and I'm going to show you data for both of those. Okay. The first one, and it was actually almost the first thing we saw within a few days of starting our traverse, which was a month or two after landing, because they spend that first month or two checking out all the instruments, making sure everything's working and doing a lot of testing or whatever. So, but once we started going, literally the first thing we saw was this, and the fluvial geomorphologist on the team went crazy when they saw this. And the reason is they really love rounded pebbles. And this is an example. We've all seen these in riverbeds, you know, in our life at one time or another. And the fluvial geomorphologists will tell you they just don't form by any other kind of process. By wind erosion doesn't form these rounded pebbles. This means there was a stream with flowing water on the surface of Mars in the past. So that was very exciting. And that was in that midpoint. And then the next one will be in Yellowknife Bay itself. It was such an interesting area for lots of reasons. They drilled a couple of holes. And when I say that, remember, we're talking about drill holes that are 6 centimeters. That's really nothing compared to what we do on Earth and what we need to do on Mars. But that's, you know, we're just starting out here. And this is an image of that. And, you know, it's so interesting because the red, we discovered that the red that we see on the surface of Mars everywhere only goes a few millimeters into the subsurface. As soon as you get just a millimeter to, the material coming out is a grayish green color. On Earth, that means it's less oxidized, and that probably is the same thing on Mars. So that was very exciting. And by the way, that's been the case for most of the other drill holes that have been drilled since then. In the 10 years that Curiosity has been now on Mars, there's been many, many other drill holes in lots of different environments. Almost all of them show this same thing with almost immediate switch in color. So they took some of this sediment here and put it in one of the instruments on the Curiosity rover called the ChemMin, as in chemicals and minerals, ChemMin. And it's an X-ray diffraction instrument that can tell you the mineralogy. And what they found is that this material had more than 20% clay, which was very exciting. Of course, that's what we're looking for. That's where organics are trapped usually. If there's biosignatures, they should be in materials like this. But it certainly tells us, it's another piece of evidence that there was abundant water there, because clays do not form in dry environments. So that was very exciting. And the other exciting thing about it was this area, because it's covered with the oxidized iron, didn't show any evidence of clays from orbit. We do have an instrument that gets mineralogy from orbit, but it really has to be at the surface. And even a few millimeters of rust will cover up that signal. And so there may well be lots of other places on Mars that are more interesting than we know if we just get below the surface. So that was another exciting thing about that. So, and then after going to Yellowknife Bay, then we turned and went west. And I was with the project for 5 years till the end of 2016. And this was one of the exciting areas that we found in subsequent this. I think this was Sol 900. Yeah, where the Sol is a Martian day, which is like a half an hour longer than an Earth day. So this is approximately 900 days later. This is an area of huge veins everywhere we looked, and we call this Garden City. But the point of this is that veins like this only form when there's subsurface water coming up faults and fractures. And so now we have evidence for water on the surface, and we also have evidence for water in the subsurface. And now just to tell you where Curiosity's been, here was the landing site. And there was our little traverse to Yellowknife Bay. We were actually there for quite a long time, till at least 6 months had gone by. But then the project, they started moving and came all this way. They are now they've come through the dunes, crossed over this fence, which is now called the Vera Rubin Ridge. It's very interesting geologically, but I won't be talking about that. But they've come to this area that had clays from orbit. That means they're right on the surface, and that might be even more abundant than they were in Yellowknife Bay, where we didn't have any evidence for the clays from the surface. And they're still looking at that data, and they're right here now, and they're just about ready to maybe come up this channel. So that's where they've been, 10 years on the surface. I think somewhere on this slide, it shows you how many miles or kilometers they've traversed. It's I think 17 or 18. I can't see it because some of the
17 and a half miles.
Okay, good. Yeah, I think it's at the top, and I've got the Zoom thing up there. Okay, so that's Curiosity. The overall conclusions are that there was abundant water. There's even evidence for a long-lived lake. And I won't go into the evidence for that now, but it looks like there was quite a lot of water there. And from the mineralogy, from the different minerals that they've measured, and there's other instruments that measure elemental compositions, elements as opposed to minerals, we know that all the key elements for life are present there. So Mars definitely was a habitable planet early in its history. Okay, so that's Curiosity, and now I want to talk about Perseverance. It was the next rover mission right after Curiosity. It landed in 2021, February of 2021, so it's now been on the surface a little over a year. And just to remind you, the location is here. It's actually not far from the dichotomy itself. The primary goals of the Perseverance, the mission itself is often called Mars 2020 because that's when it launched from Earth in 2020. But people talk about it as the Perseverance rover. But the main goals, instead of just trying to establish habitability, are to actually look for evidence of past life. In other words, we're going to be looking for fossils of microbial life, more than likely. We don't think there are any dinosaurs on Mars. But evidence of life in the past. The exciting thing about Perseverance is that they are actually going to collect samples. They're going to be called cache. They're going to be put into special containers, and they're going to be brought back to Earth in a subsequent mission. It's an enormously expensive prospect, and it won't happen until the early 2030s, but they will be brought back to Earth, and then a huge amount of detailed study can be done. And they're going to test oxygen production from the Martian atmosphere, and what's called in situ research utilization. You see that term a lot. So that's Perseverance. And now I'm going to zoom up in this area here. This is called the Isidis Basin, and we're going to zoom up. I'm just going to show you what that area looks like and why they chose it. Okay, here's the Isidis Basin. Again, this is a topographic map again from MOLA data, and the Perseverance rover is actually in a crater called Jezero crater, and that's right here. It doesn't look like much there, but it'll look better in the next image. Oh, let me just go back. I forgot to mention, this area is where the Beagle lander crash landed. It was a European Space Agency lander that I think, I can't remember now the actual date, the early 2000s, but it wasn't heard of for the longest time, and it was years before it was actually located by high-rise imagery. But the Beagle crash landed here, which is approximately where it was meant to be. It just didn't have a soft landing, so that's a bit of a shame, but that's where it was. Okay. So this is now Jezero crater, that crater that didn't look like much there. And the landing site, again, they had to pick a flat area, but the landing site is here. But the objective, if you see this channel here coming in here, and then you see what looks like to human eyes, a delta. And that's what it is, which you'll see even better in the next image, which will zoom into that area. So here's that channel, and here's what looks like the delta. And this is mineralogy from orbit, and that's from that what the instrument that's called CRISM instrument. CRISM stands for Compact Reconnaissance. Anyway, it's a spectrometer for mineralogy called CRISM, and it's on Mars Reconnaissance Orbiter, and it gives us mineralogy from orbit. That's when I was talking about clays from orbit. And we know that there's carbonates here and other sorts of mineralogies here, but here's our delta. And right in front of the delta is what we call bottom set beds. At least on Earth, deltas usually form on a muddy platform. they're often places where organic matter is abundant and where microorganisms can live. So the actual landing site was here, and I think just before I show you where they are, this is a picture of a piece of equipment that's going to be used for caching samples, for collecting little cores. They're going to drill some of those 6-centimeter cores, just like the Curiosity rover, but they're going to be cores, not powdered samples, little solid pieces of rock, and they're going to be placed in here and then buried, I think, in a place where it'll be protected from radiation or some way sealed. And then a subsequent mission will go to Mars and we'll pick it up and bring it back to Earth. And so that's very exciting. That is a very on the edge project. So it's very, very exciting. So, okay, so this is the landing spot. And of course, now they've been on the surface only a little over a year, but you can see where they landed. These are all the different sols, and they're about here now, about here. They're just now getting data from the bottom set beds and the front of the delta. And then they're going to try and go up to that area of carbonates, because one of the types of fossils that I'll talk about later could well be in an area with carbonates. So that'll be interesting. So there's not as much data from this, but you're going to be hearing more and more about it. And I did just want to mention 2 types of data that I think you will be hearing a lot about. This is the Perseverance rover. You can see it looks a lot like Curiosity. It has a mast, and that's where all the cameras are. Most of them have been improved slightly from what Curiosity had. And it has an arm. And on the arm are various instruments and the drill, just like on Curiosity. But there's 2 instruments here that were not on Curiosity, the Sherlock instrument and Pixel. And you will probably start hearing about these. Sherlock stands for Scanning Habitable Environments, with Raman and Luminescence for Organics and Chemicals. This is really important because Raman is one type of spectroscopy that can detect organics, and it's the only instrument that can actually detect it at a microscopic level, and we can see where it is in the rock and that it is organic. We can identify that, so that's very exciting. Pixel is another instrument that it's an X-ray spectrometer, and Pixel comes from all this planetary instrument for blah, blah, blah. But it can identify chemical elements at a very small scale, so they can even see a grain of salt. So they're going to know what they see to a very, very high degree of resolution. So between these 2 new instruments on the Perseverance rover, if there are biosignatures there, we may well be able to see them or get a hint of them. Okay. So biosignatures. I wanted to spend a little bit of time and talk about that. So there's basically 3 kinds: morphological fossils, like this, but we don't think there's going to be a dinosaur on Mars. Chemical fossils, and by that we mean patterns of compounds that are produced by life on Earth that aren't produced by other processes. So there can be chemical fossils that tell us that there was life there. And methane is sometimes produced by organisms. It can be a chemical fossil, but methane can be produced by non-biologic processes as well. So it's just a start. And finally, there can be mineral features that are created by life forms and aren't really created by other processes. And the most important ones are called stromatolites. And these are domes created by the growth of microbial mats that are then solidified by lithification. The minerals evaporate, and you get these layers, alternating layers of minerals and organic matter if you look at a cross section of one of these. So one of the key sites on Earth to study modern day stromatolites is in Australia. Many people like myself have been to Shark Bay. It's a very exciting place to visit. And this is a picture of that. So we have modern examples of this, but we also have examples of that in our own fossil record on Earth. So let's first talk about morphological fossils, though. On Earth, we have morphological fossils going back to 3.5 billion years. These are some of the better preserved ones. You could see what look like little chains of cells here, and these are filaments. They go in and out of the sediment They're confirmed to be of organic matter. So we know that these are morphological fossils. And we have stromatolites, and here's a cross section of one from a 2 billion year old outcrop. But when you actually make a very thin slice of this and look at it with a microscope, you can see that those layers look like this. The dark material is organic matter, and the light material is silica. If you zoom up even farther into one of those dark areas, what you'll see here is that there's filaments everywhere. They go in and out of the section, and there's a variety of different kinds, but all of these layers are made up of microfossils. So stromatolites are important. They're some of the oldest evidence we have of life on Earth, and they usually form in carbonate environments. That's why the Perseverance rover is going to try to get to that carbonate zone. But life is not always easy, and by the time you get to the oldest possible microfossils on Earth, they're not nearly as well preserved as what I've just shown. In fact, if you looked at that, you wouldn't even be sure it was organic matter. You wouldn't know, even if it were organic matter, is it just organic matter pushed to the edges of crystals? You might wonder about that. So one of the things we do is to study well-preserved microfossils with something we call nanosims. Nanosims, SIMS is secondary ion mass spectroscopy, and nanosims is secondary ion mass spectrometry at a tiny, tiny scale. And some of those well-preserved microfossils are shown here, and we looked at a little area like that, blown up here, with nanosims, and we could confirm that it's made up of carbon and nitrogen, and that the two abundances parallel one another. This is the nitrogen to carbon ratio. So we determined that when we have some fossils that we feel certain are really organic microfossils of microbial ancient life, we saw two characteristics. The material is aligned into probably wall-like envelopes. That's one of the most basic characteristics of life. It's packaged in an envelope with a boundary. And we see that nitrogen and carbon follow each other. When they're low, they're both low. When they're high, they're both high, the abundances. And this observation, when we look at other kinds of organic matter that looks like it's non-biological, we don't see this relationship. So we think this gives us a criterion that can help us to evaluate things like that really look awful. And in fact, we have actually done that. And I have that in some of the backup slides if you want to see it later, but we have done that. And in fact, it looks like these are fossils because we have that same relationship with nanosims, the carbon and nitrogen, and we confirm that it's organic matter. So, but the interesting thing about doing nanosims and being able to interpret poorly preserved or uncertain specimens is that these are the kind of instruments you need. This is a nanosims instrument in Paris, which I used many times over the last decade. And this is a SIMS instrument. This is my colleague and partner from Penn State. We've used both of these on some of these uncertain microfossils. You can see that there's no way you can take those to another planet, that you have to bring the samples back here and study them. And that's a good reason to bring samples back to Earth. So, in conclusion, 3 or more billion years ago, Mars may well have been a pale blue dot, like Earth is today. We have evidence for rivers and glaciers, maybe an ocean. And so certainly microbial life was possible. But today, Mars is the red planet. The surface is not habitable. We feel like liquid water is essential for life on Earth. We may find biosignatures of past life. We may find that on the surface or near the surface, but there is a chance that life could exist in the subsurface, even life today, of microbial life. Because in the subsurface, all planets get a little warmer with depth because they have hot cores. And so there may well be a place where there's liquid water. It's feasible there, not impossible. So with that, I'm going to try and take you on a tour of Mars now and show you some of these things on Google Earth. It's more exciting to see it that way. And I would encourage all of you to feel free to ask questions at the end, or you can even pipe up while I'm talking, but let's see if this will work. Okay, so I'm going to go to Google Earth now. And I have to tell you that, just a second, let me get rid of that. Okay, get rid of that to back. Okay. I've been having a little trouble with this myself during the day, so I'm not sure it's going to work the way I hoped it would. But this is a similar topographic map of Mars. It's a global map, so you know you're seeing it as a globe. And for those that you don't know, any of you can access this. You just go to Google Earth, and I'm going to move this away. Maybe I could move it. Can I move it? Oh yeah, I just want to move it away for a second. So are you seeing this as I'm moving it? Does it?
Mm-hmm. Yeah, we can see that, Dorothy.
Okay, well, I just wanted to point out, if you can all download Google Earth, it's a free piece of software to your computers. And to get to Mars, you just click on this and you choose Mars. You can also look at the moon, but it defaults to Earth. So you go to Mars, and under global maps, this is the colorized map, but it's the elevation map, the topographic map. And it's very much like what I've shown you, where the highs are the reds. And here's the Tharsis area with that big shield volcano. By the way, Mars has the largest volcano in the solar system. It's here, it's called Olympus Mons. It goes to like 16,000 meters in elevation. So it's amazing. But here you can see the scar. Here you can see all those river channels. You can zoom up. And there's higher resolution data sets. So that's where I've been having a little trouble. So I'm not going to do it quite yet. But you can zoom up. You can see all those rivers and flowing into that area. I'm going to show you a few other things before I branch out, because I'm not sure it's all going to work today. There's what's where Perseverance is, etc. Okay, so I showed you that. You just click on that. Okay, to keep north up. Okay, so now I'm going to show you a few other things. First, I'm going to show you some what we call fluidized ejecta on Mars. Fluidized ejecta, that's from an impact crater. Okay, so I stopped it. Here's a good example. I stopped it because this data set is pretty coarse in resolution. So when you get up real close, you don't really see too much. Here's the crater. I'm going to try and switch to a higher resolution data set that will show you that. And that's where I had trouble. I can switch to it, but what happened was I couldn't switch back, which would be a shame. But the higher resolution that you might want to try first is the context, CTX. You just click on it like that. And it takes a while for it to come in. That's not context. Here it is. Now you can zoom up and see what we call fluidized ejecta. In other words, when this crater impacted into the surface, it looked like mud flowed out, and you know what? You'd never, ever see this on the moon. There's ejecta in lunar craters, but there's spiky arrows of debris. There's nothing that looks like these fluidized flows. So this is very typically Mars. And I thought that was interesting. Now, if I go back to colorize, let's see if it goes back. Oh, it did. Great. Okay. I'll show you a few other things because it's fun to switch between the two. Let's show you the crater. Let's go to the glacier. And you can mark positions, obviously, and then go back to them. And you can name them anything you want. Oops, I stopped it too soon. Let's go to the glacier. Okay, let's see where we are. First of all, I want to show you where we are on the planet. It looks to me like we're close to the dichotomy. We are. A lot of glacial deposits have been found right at this boundary. And I'm not really sure. Maybe there was more fluid here and the elevation was getting higher. Maybe that's where glaciers formed and flowed than to the south. I'm not sure, but so this is where the glaciers. Now, if you zoom up as far as you can, you're not really seeing much at all, right? I'm not seeing much at all, but if you switch over to the context data, again, that's not the, I know that the context is always black and white. Still doesn't look like much, but for those of you with good eyes, you might start seeing something that looks kind of familiar.
Yeah.
And that's that glacier that I showed you. And you can get really high on this. Whoops, that's about as high as you can get in resolution. But now that you've seen that and you're in the area, what you're going to see are these flows everywhere. You don't see that in other places on Mars. So I think ice was flowing everywhere in this particular region. And now that you've seen the one, if you look around this platform, you'll see more glaciers. See some, they're not quite as dramatic as that one that I chose, but here's that, those linear grooves. This is called lineated valley fill, and here's the terminal moraine, and I think there's even more around the edges. But so that's the glaciers, and there's other areas. I'm just showing you one area. You can see some of them. They're flowing off this high point here, this high platform into the low areas here. Pretty dramatic, if you ask me. Okay, so that's a glacier. Okay, let's go to Jezero crater. Okay, so here's Jezero crater, and I already showed you that, but I'll just show you how you can zoom in yourself. And by the way, I've got the grid on here, so you can see where the equator is, whatever. But I'm going to get rid of it. You just go to view and you unclick grid. It's just a little bit cleaner image. It's not so distracting. And what you see here, these are strips of context data from Mars Reconnaissance Orbiter. It doesn't cover the whole planet, but it covers much of it. So, that's what you're seeing. And it's on what we call visible imagery from another spacecraft, and that does cover the whole planet. So that's that orange background. So the context is excellent data, and really just came into being in the last 2 decades, less than that even, maybe about 15 years. So this is Jezero crater, and there you see that channel, and there's that delta, and you can zoom up. And sometimes if you want to even possibly look at higher resolution data, you can go down to this tab under layers, under spacecraft imagery. It tells you all the different things that you have, and you can click high rise. And all of those are the footprints. Since this is a landing site, there's lots of images here of high rise, but you could click on one. I better just click on this one, and it will take you to another page where you can actually see even higher resolution data. It takes you actually out of Google Earth. See if this works. Yeah, and it shows you some, but then you can actually, there's a way of looking at the highest resolution. You have to have a special software to do that, but you can even just look at JPEG. Let's try. Let's try this. Let's see. Oh, so there you can get some other images like that. So, and it's just kind of exciting. But I'm going to go back now and get rid of that. So that's Jezero crater. So I'm going to take you to this one now. I should have done that when I was on the other side of the planet. We are back in, let's go back to the color. The colorized kind of tells you where you are. So we're in this area, I'll just kind of zoom out a little bit. There's the scarp, there's all those rivers. There's the dichotomy coming here. And this area is kind of unusual. It's called Arabia Terra. It's not really known. there's no other place on the planet that looks like this. It could have been a shallow shelf on the edge of an ocean. But there's a lot of craters in here that have tremendous buildup of sediments. And I wanted to show you this one of them. See if we can get to it. So if you have a location, you can get to it. Okay. So now we're going to go up. And again, I'm going to switch over to the context data. Let it do its thing. Okay, here it came. It takes a while to come in.
Face upside down.
Mhm.
And some of you may be seeing this as a bump rather than a crater. It happens to everybody. With time, it goes away and craters look like craters, but it takes a while, I have to admit. This is the crater. This is the inside of the crater. These are enormous black sand dunes. I imagine if you were on Mars, they would be so beautiful, almost indescribable, black sand, because there's a lot of volcanics on Mars. Mars is very much a volcanic planet, and black sand comes from all of the rich sands. So that's what happens in volcanic provinces. You get black sand beaches in Hawaii, but these are huge and it's interesting. But in this area here, you can see these tremendous layers. Now, the reason we can see them is that all of that black sand is in the lows, but look at that layering. It's phenomenal. And these areas haven't actually been studied too much yet, but they're just amazing. And I think there's a place here where you can see some of that layering going in those ridges. That's on track. Maybe. If you just keep going up, you see more and more stuff. It's just amazing. So here you can see some of those layers are nearly horizontal layers. So the tremendous amount of alternating wet and dry or windy and not windy, whatever, tremendous history in these craters here. And this is true in a lot of the craters in that area, Array of Terra. So I'm going to show you another area. It's an area that I've worked on a lot, and I'll go back to the colorize and show you where you are. It's an intriguing area. So remember I said that Pathfinder was here, and this is where all the coarse grain material would be, and the fine grain material would be farther into this lower area here. That's the area we're going to look at here. You don't really see anything at all. Oh, I will show you one thing. Wait a second. So I am showing you a lot more science. I hope that's not too much, but this was a huge bulge and uplift that cracked the crust. But because of that, it also formed a bunch of faults. It pushed material in front of it practically around the whole planet. There's a hint of that here in all these linear ridges. 1, 2, then there's some in here. These linear ridges are thought to be buried, what we call thrust faults, where the crust was just pushed by that huge uplift. And in this area, if you zoom up, so I'm going to be looking at this area, but now I'm going to look at a different kind of data because it's really dramatic. This area, well, yeah, I'm going to look at nighttime infrared. This would be from the Mars Odyssey spacecraft. Nighttime infrared shows you areas that are cool and areas that are hot. It's kind of like thermal inertia. It's like when you go to the beach. When you go to the beach on a hot day, the sand is hot, but if there's a rock there, it's cool. And at night, the sand is cold and the rock is warmer. If you've ever lived at the beach or near a beach. And that's what we call thermal inertia. And this nighttime infrared measures thermal inertia, as I remember. I just want to show you this area. Let's just go back to the colorized for a second. You'll see that you don't see anything here. But when you look at this, there are thousands of these spots. And they're all over the area. and only in this area. They're not in the highlands anywhere. In fact, we've measured these spots. There's something like 40,000 of them in this area where the fine grained mud should be. A lot of work has been done on them, and a lot of people think they're like mud volcanoes on Earth. And one of the reasons is that they have this dark response in the nighttime infrared, the way fine grained materials would be. It's like something has brought up fine grained materials. And if I click high rise again and find a high rise image, there won't be nearly as many as a landing site because they cover that with high rise. But like, here's one that goes over some of these images. Maybe I can just show you what they look like. I'll just pick, there's two actually there. Takes you right to the high rise site, and I'll just pull the JPEG, maybe the map projected one. See if we can. And you can see that these are mounds that this is visible in high res is visible, so they're white, so it's like a different kind of chemical, but we know it's a fine grained material. It's like mud. So that's kind of an interesting area. It's an area I've been working on for maybe a decade, and it's an exciting area as well. Well, I think that's about all. I think I've showed you everything I want. Well, I suppose that maybe, okay, one more thing here. We'll go back. Oops, I should have. Okay. Here's the Cerberus fossey, but you can see there's a lot of high-res images there. I'm going to get rid of those if I can. These are some of the most recent faults on the planet, and actually it's pretty interesting because these are areas where they think actually floods, some of the most recent floods on the planet have come out. So for some reason, Mars is more active here today than other areas, which are generally not active anymore. And so that's another area of high interest. You have to get up really high in resolution to see evidence of that. And you can see here where these faults have faulted right through impact craters. It's an interesting area. Well, okay, I think that's about all I plan to say. I'm happy to take any questions that you have at all. We could stay on here, or we can go back to the presentation. I had some backup slides showing other things, but depending on your questions, we can stay here or whatever you like.
Well, thanks very much, Dorothy. We have one question in the chat, and
Okay.
if anybody on Zoom has questions, you can use the raise hand button and I'll call on you. And if anybody here in the room has a question, just raise your hand. Carol has a question. What happened to the water?
What happened to what?
The water.
Oh, good question. That's actually a great question. A number of things happened to it. Mars, early in its history, it had a denser atmosphere, but the planet lost its and it had a magnetic field like the Earth does, which deflects some of the solar wind, which are ionized particles coming from the sun. It deflects them to the poles and kind of protects much of the planet from this ionizing material. Mars has a smaller core than Earth, and the magnetic fields are produced by the liquid part of an iron core that produces the magnetic field. So Mars's core being smaller than the Earth, it froze sooner than the Earth. Earth still has the liquid iron, so we still have a magnetic field, but it's thought that Mars had a magnetic field, but it lost it very early on, and that allowed some of the ionizing radiation to come all over the planet, and it broke water molecules into hydrogen and oxygen, then which got lost to space. So a lot of it just went into space from the solar wind, basically. Some of it sank into the ground. There's a very thick cryosphere, which is ice in the subsurface. Some of it is protected in the ground from that solar wind. The cryosphere is over the whole planet, so some of it is below the surface as well. It's just that on the surface, it just freezes and sublimes right away. So it doesn't last on the surface. So some of it is protected below the surface and a lot was lost to space.
So Dorothy, would you stop the share so we can see you on screen?
Okay. Okay, so let's stop that.
There you are. Okay. All right. We have a question in the chat. Nels wants to know, what are the current speculations about the source of oxidation on the surface?
That's also a good question. You know, I remember when I asked that question, when I was just starting this, that was one of the first things I asked, because there's not a lot of oxygen there, but there is peroxide and perchlorates. Those are two oxidizing chemicals, and they're thought to be part of that problem. And there might well have been more oxygen early in the planet's history. But yeah, I think it's probably mostly the peroxides. There's a little bit of peroxide in the atmosphere of Earth too, but not nearly as much as on Mars. So some of it may have been oxidized by that.
Okay, we have, go ahead and ask your question.
Why is there no tectonic movement on Mars?
You know, these are all good questions. And I'm not sure I can answer that too well. I know I've read some papers discussing the possibility that Mars doesn't have plate tectonics because it doesn't have as much water in the subsurface as the Earth did. But I'm not really sure about that. And I think that's a great question.
I would hazard a guess that because it's cooler on the inside, the mantle doesn't have anything to float around on.
I think that's part of it. And some people talk about Mars as a stable lid planet, as opposed to one where the lid is moving around. That's maybe one reason why Tharsis, that huge area of sheet volcano, came up, because the planet got hotter and hotter and hotter in the subsurface, and finally it all came up. So the lithosphere on Mars seems to be a little thicker than that on Earth. So it's just reacted differently, as well as perhaps not being quite as lubricated. But that's a good question, and I don't think I've answered it as well as it might be, and it could be that it's just not quite understood yet.
So there's another question in the chat. Chip would like to know, what do you think of Elon Musk's plans for Mars and his chances of realizing his vision?
I don't know. You know, I initially was really excited by SpaceX and what they were doing, and I am excited by the fact that they have reusable rockets. You know, they come back down and they land, and some of that has been very exciting. And everybody at my institute, the Planetary Science Institute, when some of those images came of those things turning around and coming back and landing safely, said, we are looking at the future. So that was very excited. I don't know if his plans involve the idea of changing the climate on Mars, climate change, essentially. I think without a magnetic field, that would be almost impossible. And until recently, I thought that was not ever going to happen. But I actually read an article recently that talked about maybe a way of establishing an artificial magnetic field from pole to pole. And I've forgotten the details, but if you could establish a magnetic field, you might be able to change the climate. And I don't know if his plans include that, but I'm guessing they might. Other than that, I don't know what his other plans are. I really hate the fact that he put a car in orbit. I thought that was the stupidest thing. It adds to the debris. I mean, there's already a lot of debris, and that bothered me. I wish he wouldn't have done that. But he's clearly an exciting person, and there's good and bad there. So.
Okay, we got a question in the room over there.
So regarding the elevation map, how did one determine like what sea level was, or whatever you call
Well, people, the first people that thought there might be an ocean looked in that area of the dichotomy for things that are common at ocean boundaries on Earth. And you get cliffs forming and you get shorelines, and there are things that geomorphologists look for. And there was a study a long time ago talking about shorelines, and they established 3 possible shorelines looking at different areas where they had what shores do on Earth. So that's one way, and that's the color differences that you see are based partly on that, but the dichotomy is really clear. If there was an ocean, probably the largest extent of it would be where the dichotomy is today. Although the dichotomy is moving southward, there's a lot of stress there. The crust is much thicker on the highlands than the lowlands. So there's stress at that boundary where it's thick crust and thin crust, and it keeps evidently moving to the south a little bit. So it might have been maybe not quite as far south as we're seeing the dichotomy today. But so that was the first way of doing it. And, there's been some discussion of that. Not everybody believes that work. Other people have come up with other ways, and people said, yeah, but you have to move Tharsis out of the picture and then you'll understand it better. So those kinds of discussions. But I think there's a lot of evidence just from other kinds of data too, with that many rivers, the amount of water flowing in a huge area of lowlands, plus the geomorphology of fluidized crater ejecta that are mainly in the lowlands, things like that, it's a body of evidence that suggests there was an ocean there. And then there's the possible different elevations where they see cliff faces and ocean boundaries, similar to what's on Earth.
Okay, Tracy, go ahead.
On Earth, we know that we have this molten core. How far into the center of Mars can we see or guess what's going on? Like we know on Earth, we have a mantle and a core, and we know it's molten. Is there molten stuff in the center of Mars, or?
Actually, the one thing I forgot to show you was what's called the InSight mission. It's in an area near that Cerberus Fosse that I showed you just right at the end. It's a very flat plain. It's a lander mission. It's almost finished now. It's been on the surface for a couple of years. It's a short-term mission, but the whole objective of that was to get seismic data that would tell us more about the core mantle structure and how big the core is, how big the mantle is, if there's a liquid part. So that data is being processed right now. So there'll be a lot more information about that coming from InSight. InSight, they also had they were going to drill down 2 meters and get the heat flow of the planet. That's something that we don't really know. That's the instrument that didn't work, and they never got more than a few centimeters. It got stuck and it wouldn't drill. And I'm not sure if they really truly understand that. They worked on it for over a year, I think, to try, what they have a mock-up of all the instruments at JPL, and they do, when there's a problem, they do testing with they have the exact duplicate instrument. They do testing with to see, how they can make it work or get better information. And in many cases, they've been able to solve problems. Curiosity, for instance, had trouble with the wheels. They were just falling apart. They were getting holes in them. And it was like, oh my God, this is not going to last very long. And they did a lot of testing at JPL, and they found that certain kinds of topography that you could see from orbit must have had much more pointy rocks that we really weren't aware of than others. And so they changed the route to avoid those areas. They also found out that when the rover went backwards, it didn't get as much damage in the wheels. They did all sorts of things, but they solved that problem because the rovers lasted now for quite a long time. But so that's what they do. So I think the results from the InSight mission are just coming in, and I actually don't know what their conclusions are yet.
Thank you.
Okay, a question in the chat. How fast does the wind blow during the global dust storms?
That's a good question. but I don't have the answer at all.
One thing I do know, that scene from The Martian, the movie The Martian, where the wind blows and it blows over his equipment,
Yeah,
that apparently could not actually happen because even though the wind blows fast, the density is very, very low.
that's right. That's exactly right. Actually, there have been various articles written about how the wind can form these huge dunes, because even that's a surprise, but the wind must blow pretty fast, actually, because it isn't very dense at all. I will tell you that film, The Martian, because, I guess I'm presuming everybody's seen it. I don't want to say anything. I don't want to ruin it, but, they eventually find, they go to the Pathfinder site in that film to solve some of their problems. But since I've been studying that area, I remember I said I knew about Pathfinder, and then the area that I study is just a little further on where the muds would be and all those little black spots, which are fine grained materials, maybe mud volcanoes. So when the movie was starting, they actually panned in on real imagery, and I said to my husband, I said, "Oh my God, I know that crater. I know that crater. That's Pathfinder." It was really amazing. And actually, I was at JSC. They spent time. They came to Johnson Space Center and talked to astronauts, and they talked to geologists. They wanted to get it as accurate as possible. So, I was there when they did that. I didn't have any discussions with them, but nevertheless, it was kind of a fun time.
Okay. Another question in the chat: is there any useful data coming from Ingenuity, the helicopter?
Oh, the helicopter. I should have mentioned that. That is the biggest surprise of all. To be honest, it has done much better. I think it's flown 50 missions already. It's been able to fly like a drone and take images of places that they couldn't have imaged, from that low elevation. It's opened up the possibility of future exploration in ways that nobody would have imagined even a year ago. Nobody even knew if it would fly. It's even hard to imagine that it does fly, to be honest. So yes, there's all sorts of studies, some of my own included, that say we could do this if we could fly a drone, but without it, we couldn't fly a drone. And one of the things I also forgot to mention, if you noticed when I showed you all the rovers and landers, that most of them were near the equator, one way or another. They were sort of near the dichotomy, on the dichotomy, just a little bit north, just a little bit south. There was one or two missions that were far north, but they were short-term missions. The thing is, when you go so far north, it's too cold for these long-term rover missions that go on for years. The winters are just brutal, and some of the equipment wouldn't work. So that's why some of the areas that have high potential for great geologic interest might be sites where there's a tremendous amount of organic matter, maybe biosignatures, haven't been explored yet, but they could be explored with drones or helicopters. So it's opened up a whole new area of thinking. So it's very exciting, actually.
Okay, I've got some questions in the room. Okay, we got a young man back here.
Does the mountain on Mars affect the atmosphere in any way?
Does the mountain on Mars,
Affect the atmosphere?
does the mountain on Mars, the big volcano, Olympus Mons, does it affect the atmosphere in any way?
I don't actually know the answer to that, but I would think it must. Honestly, I know people study the winds, they know exactly where they go, and I'm not one of those people, but I feel certain it must. I don't really know the answer to that.
Okay, sorry. Now I saw another hand over here. Yeah.
With all the craters impacts on Mars, at that point, when that was happening, over what period of time preceded the atmosphere, there mustn't have been an atmosphere to let all the meteorites and asteroids get through, like on the moon. And then, so that period was preceding the atmosphere, and where did the water and what was the air density when they had water? I mean,
You know, I'm not sure of your question, but
The atmosphere on Mars are not having an atmosphere allowing for all the crater impacts.
right. Early on, Mars is thought to have had more of an atmosphere when the planet was a little bit warmer and the rivers flowing. It had to be a little bit warmer than it is now. Although some people think it was just interludes of warmth in an otherwise cold climate. But nevertheless, it was probably certainly wetter and warmer than it is now. It had an atmosphere initially, and there's a lot of chemical data on to suggest that it had a denser atmosphere early on. A denser atmosphere would prevent some of the smaller meteorites from coming in. You know, they would burn up in the atmosphere. The big ones would still come. And early in the history of all planets, there was a lot more chaos in the solar system. All planets were bombarded by big bodies early on. When Mars lost its atmosphere, then all sorts, even the small ones, can come in. And so they actually age date parts of Mars by the number of craters they have. Areas with more craters are generally thought to be older, and that's basically based on data from the moon, where they actually got samples from different areas and they brought them back to Earth, and they did radiometric dating, so they know how old those areas were, and then they could look at the amount of craters. So there was a whole area of age dating for the moon that established these crater counting boundaries for different ages, and that's applied to Mars. It certainly won't be exactly the same, but it's a first pass guess as to what the age would be. So the youngest craters on Mars don't have the fluidized ejecta because it's gone from the surface, and the near surface is probably deeper. So the youngest and smallest craters don't have fluidized ejecta, but they have to be big enough to go deep enough to get into an ice-rich zone. So that's another way you can tell a young crater, is that it usually doesn't, it looks like a lunar crater, actually.
Okay, any other questions? Over here, yeah.
When you're looking in the spots that could have water, like the larger spots that could be like an ocean spot, as opposed to the smaller ones that could be like a lake spot, are you looking for different indications in the same way that you would look differently here on Earth between a saltwater place and a freshwater place?
Yes, actually, certainly in Gale Crater, where they got a lot of data, they found that the minerals that were there were minerals that would form in a neutral setting, and wouldn't be particularly saline. There haven't been a lot of salts found on Mars, which is interesting, and that's a continuing question: where are the salts? But some areas have minerals that would form under acidic conditions, and some under more neutral. Curiosity, all of the mineral assemblages that were found would be in a neutral water chemistry, so it wouldn't be too acidic or too basic, and that's another reason they think it was habitable. But other areas have evidence for it being acidic, and those are some of the shallower areas, not a big crater. So there certainly were lakes. There's a whole system of big craters that they thought were all lakes at one time in that area where all those rivers flow into that big basin that I showed. There's some big craters that were part of that system, were probably filled with lakes at one stage. And they look at the strata in the side of those channels too, and they could get an idea of what kind of materials made up those older strata that were buried, but we can see them a little bit in the channels. So, you know, that's another way of looking at some of the older material.
Okay, there's one more question in the chat, Dorothy. And in reference to the dunes that you showed us earlier, the sand dunes, and Nels wants to know, it seems odd that the dust is not filling up the lower areas of those sand dunes. So he's thinking that maybe the wind is blowing dust, and why is it not collecting in the valleys?
You know, it does do that in lots of places. There are dunes of all sizes in every every place that I've looked at. But the dust would be the finest material. Dunes are usually made of sand grain material. Dust is even a little finer. So maybe that little bit of wind in some areas, depending on how the wind flows and eddies, moves it out of maybe where dunes form, at least the ones that I showed, the dust doesn't collect there. But if I had Google Maps still on, I could show you the dust coming out of some craters where we know the wind flows in certain directions. You could see a dust shadow coming out of those craters. You know, you could see it in certain kinds of imagery. So the dust does move around, but it doesn't fill every low, but it fills a lot of them. It probably just depends on where they are.
Do the dunes move like they do on the Earth?
They do. And in Gale Crater, where Curiosity is, they've seen because they have so much images. You know, they have a lot of those high-res images. They have some of the same areas that were taken 2 or 3 years ago, and they could see that, oh, the dunes have moved. So yes, they have evidence for that, but they didn't know that until they got that recent evidence. Yes, the dunes are moving just like they do on Earth.
Okay, any more questions? Everybody's satisfied here in the room, and I don't see any more questions on Zoom either. So Dorothy, thank you very, very much. This is fascinating.
Well, thank you. I enjoyed it as well. I enjoyed it very much.
Great. Okay, I'm going to stop the recording. So don't say anything important from this point on.
I won't.